Thanks for the organizer for giving the opportunity. So the focus of my talk is the cavity-induced dynamical gauge potential and its physical consequences. So, okay, yes. So reaching the quantum degeneracy in atomic gases has opened a new direction in many-body physics. So for instance, so by loading the ultra-cold atoms into optical cavities, to the optical lattices, one can mimic solid-state crystalline material. And one of the most notable observations in this setup was the superfluid to Mott insulator phase transition. However, these quantum gases suffer from one major drawback, and that is they are charge neutral, and they cannot couple to the gauge potential as charged particles do. So this basically limits the amount of amounts of the phenomena that one can explore in this system. But that said, a plethora of proposals have been put forward to simulate the gauge potential for ultra-cold atoms. So almost a decade ago, synthetic spin-orbit coupling and synthetic magnetic field were realized for the ultra-cold atoms. In particular for synthetic magnetic field. So the natural hopping of the atoms between neighboring sides of the optical lattice is suppressed by the energy offset between the adjacent lattice sides. And then this hopping is restored by two photon processes. And this process basically imprints phase phi into the wave function of the atoms. So by doing this, so this basically simulates the Aharonov-Bohm phase of a charged particle in a magnetic field. Again, it was noted that there is another setback in this simulated gauge potential, and that is that so these gauge potentials are static and background potentials. It means that so the state of the atom doesn't change the state of the atom doesn't change the gauge potential, and this is quite different from the scenarios that one sees encounters in a quantum gauge theories or condensed matter. So there, the gauge potential is a dynamical degree of the freedom of the system. So motivated by this, again, another generation of gauge potential, a proposal for another generation of the gauge potential have been put forward, and to simulate a dynamical gauge field for the atoms. So most of these techniques, most of this new generation of techniques are based on Faraday engineering. And recently, density-dependent dynamical gauge fields have been realized for the atoms. So at the same time of these progresses, people start to ask if it is possible to engineer a dynamical gauge potential based on different techniques without restoring to the Faraday engineering techniques. And it turns out that the answer to this question is yes, and it relies on a strong atom-matter interaction coupling. So in free space, the probability of an atom-photon interaction is much, much smaller than 1. So this means that one needs many atoms and many photons to see a nonlinear effect. However, if the radiation field is confined within a cavity, so the photon travels many times inside the cavity before leaking out of it. So this increases the atom-photon interaction probability significantly and reaches almost 1. So in this regime, a single atom and single photon is enough to see a nonlinear effect. So if the gauge potential is induced by the cavity photons, so then this would be the sensitive to the state of the atom. So if the state of the atom changes, this would affect the gauge potential. And this is the basic idea behind the cavity-induced gauge potential. So, for example, recently we showed that dynamical spin-orbit coupling can be induced for a Bose-Einstein condensate inside a single-mode cavity by using two independent Raman channels. So we showed that exactly as one expects. So dynamical spinorbit's characteristic appears in the band structure, and this band structure actually are dynamic. So as a consequence of this dynamical spinorbit coupling, we showed that interesting spin textures emerge in the system. And immediately afterward, so this scheme was realized in the Benlev's group in the Stanford. So I have to now go to this here. So, and as we predicted, they exactly see that the spinorbit coupling emerges beyond some critical threshold strengths, and the characteristic spinorbit coupling, the characteristic momentum distribution of a spinorbit coupling also emerges in the system. So, and now in our current work, so we decided to implement a density-dependent dynamical U1 gauge potential for atoms based on a simple cavity QED setup without restoring to this flocate engineering. And then we investigated the physical implications of this cavity-induced dynamical U1 gauge potential. So let's start with our proposal. So we consider two components atoms in an external optical lattice, which is perpendicular to the So again, I will go out of it, which is not possible. So which is perpendicular to the axis of a two-mode cavity. So in particular, as you can see in the right side, so sorry, I cannot use the notation, so I will just say. So as you can see in the right side, in the top figure, so if the atoms are in the lower state, they can absorb one photon from the laser A, shown with omega A, and re-emit it to the cavity denoted with JA, and then move to the right. And if they are in the upper state, spin-up state, they can absorb one photon from laser B, shown with omega B, and then re-emit it to the second mode of the cavity, shown with the GB, and then move to the left. So this is shown schematically in the lower figure in the slide. So as you can see, and then another third laser basically couples this spin up and down on side. So this system is equivalent. To a two-leg Bose-Hubbard ladder threaded with a cavity-induced synthetic magnetic field. So as you can see in the figure, so the current in the counter-propagating currents in the two legs are proportional to the photon number in the corresponding cavity modes. So in particular, the current in the lower leg is proportional to the photon number in mode A, and the current in the upper leg is proportional to the photon number in the second mode B. And the phase imprinted into the wave function is given by the phase of the photons, phi A and phi B. So as you can see in this formula, phi A and phi B, the phase of the photons, are in turn a function of the photon decay rate, palm cavity detunings, atom-photon coupling rates, and atom numbers. So when the atoms traverse one placket of this ladder, they acquire this, they feel this magnetic flux phi B, which is proportional to phi A plus phi B, and the currents and the chiral and particle currents are related to the total photon number in the two modes and the photon number difference in the two modes. But the most remarkable point is that, so the phase of the magnetic flux, which is proportional to phi A plus phi B, is affected by the optomechanical back action, which is a function of a average density, which is basically proportional to the average density of the particle. So this basically results in an average density dependent dynamical U1 gauge potential, and it has very significant consequences, as I will show in the next slides. So first, we explored the single particle physics where n is 1. The total number we have only one particle in the whole system. In this case, this optomechanical back action is quite small, and one can ignore this one and basically reach static gauge potential limit. So we identified 3 different phases based on the single particle energy dispersions and the corresponding atomic currents. So if we have a single minima, so we identify a single minima in the energy band, we identify this one with the photon balanced Meissner state. So which is shown, the currents are shown. So the currents now are shown in here. So this is similar to the Meissner effect. This is similar to the Meissner effect where in the superconductor where the magnetic flux is screened by the currents. So it is the same thing in here. So one can imagine that there is a fictitious current going up and down, and this would generate a circular current which would screen the synthetic magnetic field. Then, so if we have 2 minima with 2 minima, so we identify this one with a photon balanced vortex state. This is shown in here. And finally, we identify a photon imbalanced bias ladder phase. In this case, in addition to the pure chiral current, there is also a particle current, as there is non-zero photon, as the photon number is not the same in the 2 mode, as you can see in this figure. So then we characterize the phase diagram. So we show the phase diagram in the detuning versus the atom-photon coupling rate plane. But the interesting physics appears when we go to the many body case. In this case, so this optomechanical back action becomes really important, and as we expected now, so as we expected, the magnetic flux now depends on the density, average density. So the background color in this figure, in this phase diagram, is the magnetic flux, and as you can see that it depends in the average density. But interestingly, we also identify a regime with a nonlinear dynamics. So then we took a closer look to the physics in this nonlinear dynamic regime. So interestingly, we saw that the fields display periodic and time-dependent behavior in the phase space. So this is the mode A and this is the mode B. As you can see that, so this is a long time. So this figure shows only the long time behavior. So it shows a periodic behavior. So it is as a consequence, so the phase of the fields so changes periodically in time. So this means that if you remember, so the magnetic flux is proportional to the phase of 2 modes. So as a consequence, so the magnetic flux changes in time. And as we know from the elementary electromagnetic physics, if the magnetic flux changes, this would induce an electromotive force. And we know again from the electromagnetic, so electromotive force results in a currents in the system. Since in this case, electromotive force is time periodic, so you could see that the chiral and particle currents also exhibits a periodic behavior. So, and again, interestingly, so we see that in some parameter regime, the second harmonic also emerges. So this means that now we have a double period doubling situations. So with this,
Farokh, last 2 minutes.
Yes, I'm almost done. So with this, we show that one can simulate a Faraday's induction law for neutral particle using a dynamical instability in a cavity-induced dynamical gauge potential. So, and with this, I come to the conclusion. And so we showed that average density depending U1 gate potential can be simulated with cavities. And then as a result of dynamical instability in this system, Faraday's induction law basically emerges naturally in this case. So now the question that we are exploring and we are asking ourselves is that could we identify this periodic behavior and this emergence of a Faraday's law as a kind of a time crystal? Because this periodic behavior breaks the time translation of the system. And if we go even to higher atom photon coupling rates, we see that even more harmonics are appearing in the system. So this basically implies that we might have a chaotic behavior. And this is not very surprising because any period doubling would naturally lead to the chaotic behavior. So with this, I would like to also say that this work has been done in collaboration with Elvia Colella and Helmut Riesch at University of Calgary. And most of the calculation that I showed today, it was done with Elvia. And at the end, I would also like to draw your attention to our recent review paper in cavity QED with quantum gases. So if you are interested about the state of the art in cavity QED with quantum gases, you can consult this paper. So we give a quite pedagogical review of the field. So with this, I would like to thank you all, and I would be happy to answer any question if you have.
Thank you for a presentation, Farokh.